Look at what you can make using the Game Zero package. Or you can make something like this. Or something like this. Or even something like this. How did I do it? And how can you make your own? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
In today's tutorial, we're going to use the Game Zero package to run some simple 2D computer simulations. Rather than showing you one or two examples and then going through them in a lot of detail, I'm going to show you a lot of different examples, but only present them at a high level. That way, I can make more code available for you so that you can work through them at your own pace. For this tutorial, knowledge of Julia and VS Code is required. I'm also assuming that you watched episode 409, which gave an introduction to the Game Zero package. Okay, let's get started. Let's jump right into VS Code. In your VS Code Explorer panel, create a new folder for this tutorial. In the tutorial folder, create a new file called rungame.jl. Also in the tutorial folder, create a new folder called simulations. Inside the simulations folder, create a new file called particles.jl. Launch the Julia REPL by using Alt-J, then Alt-O. Maximize the terminal panel. Change the present working directory to your tutorial directory. Enter the package REPL by hitting the closing square bracket. Activate your tutorial directory. Add the Game Zero package, as well as the colors package. Type in status to confirm the version numbers. Exit the package REPL by hitting backspace. Minimize the terminal panel. Our first example will show circles moving in 2 dimensions inside the game window and bouncing off the borders. This example uses linear motion and assumes no gravity and no friction. It assumes collisions with the borders, but assumes no collisions between actors. In the particles.jl file, write the code to initialize the game window. Next, let's set up a variable so we can change the number of actors in our game window. We'll start with just one actor. Next, let's select random starting points for our actor. Next, we define the initial state of the actor. And just for fun, we'll select a random color for our actor. Next, we need to tell Game Zero to draw our actor. Now that we've set up our game window, defined our actors, and drawn them, we need to figure out how to get the actors to move in the game window. We start by selecting random initial velocities for our actors. Now, this next part is different. In the past 2 Game Zero tutorials, we used either a mouse interaction or a keyboard interaction to update the scene in the game window. But with these simulations, we need Game Zero to update the game window without any interaction from us. In order to do that, Game Zero uses the update function. This code looks a lot more complicated than it actually is. All it's doing is checking to see if the actor is colliding with one of the 4 corners, or with one of the four borders. If there's a collision, then this code reverses the actor's direction, either in the horizontal direction, the vertical direction, or both. Otherwise, it's simply updating the actor's position based on the actor's current velocity in the horizontal and vertical directions. Go ahead and save your file and go to the rungame.jl file and add the code to run your simulation. You should see a single circle moving around the game window and bouncing off the walls. You've basically recreated the DVD screensaver. It's not very interesting, so let's add a few more actors. In the particles.jl file, change the number of actors, save the file, and rerun the simulation. That's a little more interesting. Let's stress test the simulation with 100, then 1000 actors. This simulation looks pretty interesting with 100 actors. Let's see what it looks like with 1000 actors. It's looking pretty crowded with 1000 actors, and it looks a bit sluggish. Try reducing the radius of the circles. That's better. So you get the idea. Once you set up a model for your simulation, you can modify the variables to create multiple simulations using the same model. Okay, so that was cool. The next example builds on this example, and it adds the effect of gravity and friction to make the simulation a little more realistic. In your simulations folder, create a new file called bounce.jl. Initialize the game window and set the number of actors. Next, select random starting points for the actors. Next, define the initial state of the actors, select their colors, and then have Game Zero draw them. Next, we need to select random initial velocities for the actors. In the horizontal direction, the actors will move either left or right by 5 units. In the vertical direction, all actors will start in a stationary position with a velocity of 0. Next, we need to set the values for gravity and friction. These are arbitrary numbers that will be used to create the illusion of gravity and friction. These values do not represent any scientific value for gravity or friction. They are merely being used to either speed up or slow down the actors inside the game window. This next section of code for the update function will require some explanations. It contains a lot of conditional statements because there are so many different situations to handle. This first section of code applies the impact of friction when the actor collides with the bottom of the game window. So, unlike in the previous example, when this actor collides with the bottom of the screen, not only will it change directions, it will do so at a slightly lower velocity. This section of code applies the impact of gravity. Each time Game Zero updates the screen, the vertical velocity will increase as the actor falls, which will simulate the acceleration due to gravity. This section causes the actor to bounce off the sidewalls of the game window. This section is a little weird. I added this code because I noticed some odd behavior when values of Vx became very small. And this last section handles the normal horizontal movement of the actor. I know that was a lot of code to digest, and there's no way you're going to be able to comprehend it all while watching this video. So I encourage you to go through this code in my GitHub repository at your own pace to get a better feel for it. Save your file and go to the rungame.jl file. Comment out the line for the previous simulation, and add a line to run the bounce.jl file. When you run this simulation, you should see a single circle falling and bouncing. As the circle falls, it accelerates. With each bounce, it loses some energy, so it will eventually stop bouncing and stop rolling. Now let's try it with 10 actors. That's much more interesting. Now try it with 100 actors. Surprisingly, it's not that interesting with 100 actors. The simulation is closer to reality since it accounts for some gravity and friction, but it's still pretty far from the real world. Although these actors bounce off the walls and the floor, they don't bounce off each other, which, of course, is not realistic. Simulations are not meant to be a rigorous replication of the real world. They are useful for visualizing abstract concepts, but they should not be considered a replacement for math and science. In any event, enjoy playing with these simulations. Let's move on to simulating rotational movement. In this next example, we're going to take an actor and move it around both in a circular path as well as an elliptical path. In the simulations folder, create a new file called rotations.jl. Start by initializing the game window. We'll be using these same settings for all of our simulations. Next, we need to define the initial state of the actors. There are a lot of actors here, but most of them are being used as guidelines for the game window. For this simulation, there will only be one actor in motion. Next, we need to draw the actors. Next, we need to set values for a couple of variables that are required to move our actor around. Finally, we define the update function, which is where all of the magic happens. This update function is where you place the model for your simulation. The contents of the update function provides all of the logic and math that makes your simulation possible. These formulae for calculating the x and y coordinates around a circle can be found in the Wikipedia article on the unit circle. In Julia, you can use the cosine d function and sine d function to calculate cosine and sine using degrees rather than using radians. We're using the variable named theta for the angle in degrees. In the unit circle, A positive theta is a counterclockwise rotation. But in our game window, the vertical axis is flipped, so a positive theta is a clockwise rotation in our game window. Save your file and go to the rungame.jl file. Comment out the line for the previous simulation and add a line to run the rotations.jl file. You should see a single planet moving clockwise in a circular orbit. It's very simple to change the direction from clockwise to counterclockwise. All you need to do is change that plus sign into a minus sign. Now, you should see a planet moving counterclockwise in a circular orbit. You can reuse these formulae for calculating the x and y coordinates around a circle to find the x and y coordinates around an ellipse. All you need to do is replace the radius in the equations with the dimensions of the ellipse. For the x coordinate, use half the width of the ellipse, and for the y coordinate, use half the height of the ellipse. Pretty cool, right? For the next example, let's take a look at simulating a sine wave. As I was preparing this tutorial, I came up with an overly complicated example of a sine wave simulation using Game Zero. Fortunately, I found a much better example on the Coding Train's YouTube channel. If you're not subscribed to the Coding Train, you should definitely check it out. The instructor's teaching style is definitely compatible with my learning style, so I've learned a lot by watching his channel. In one of his tutorials, he creates a sine wave simulation using P5, which is a JavaScript library. It is surprisingly easy to translate his P5 JavaScript code into Game Zero Julia code, so that's what I've done for this example. While there may not be a lot of resources available for Game Zero yet, the Coding Train has a ton of videos on how to use P5, so I would encourage you to explore his channel since the P5 JavaScript code is relatively simple to translate into Game Zero Julia code. In the Simulations folder, create a new file called sinewave.jl. In this example, we're going to build on the rotations.jl file, so the first 19 rows are exactly the same, so you can copy and paste the first 19 rows from the rotations.jl file into your sinewave.jl file. Next, we're going to add a couple of new guidelines for this example. This next section I took from the Coding Train. Rather than trying to construct a sine wave, we're going to draw multiple circles across our game window that will simply move up and down, but not side to side. This will give the illusion of a sine wave moving across the screen. Next, we need to draw all of the actors. This next section is similar to the previous example, but instead of using the update function, we're renaming the function to update_planet. This next section is where all of the magic happens. Notice that there are no updates to the horizontal positions. The only updates are to the vertical positions, which is the same formula that we use to update the vertical position by rotating our actor clockwise around the circle. Finally, because we created two separate update functions, we need to have Game0 update the game window by using the update function, which is simply calling the two separate update functions. Save your file and go to the run-game.jl file. Comment out the line for the previous simulation and add a line to run the sinewave.jl file. Pretty cool, right? The sine wave really does look like it's moving across the screen, but if you focus on the red circle in the middle of the screen, you can see that it's just moving up and down, and its vertical position is the same as the blue circle's vertical position. Our final example is a simulation of a pendulum. I'm not gonna lie, I couldn't figure out how to build the model for a pendulum simulation. Fortunately, the Coding Train made a tutorial on how to do this using the P5 library and JavaScript. I am not ashamed to admit that I took his code and translated it into Game0 and Julia. In the Simulations folder, create a new file called pendulum.jl. Just like before, start by initializing the game window. This next section is just for the guidelines. This next section is for the actual pendulum. A pendulum is made up of two parts, a rod and a bob. The bob is the actual swinging mass, and the rod is the shaft that's connected to the bob and also connected to a fixed pivot point. For this simulation, we're going to assume that this is a simple pendulum, meaning that the rod is a weightless, stiff bar that experiences no friction and no drag. With the pendulum, the angle theta is the angle that is counterclockwise from the vertical axis, which is the resting angle for a pendulum at equilibrium. Next, we draw all of the actors. Next, we need to set up some values for gravity and angular velocity. Finally, we define the update function, which contains the physics model that will drive our simulation. That variable named ANG_ACC stands for angular acceleration, which is only impacted by the length of the rod and not by the mass of the bob. I took most of this code from the coding train, but I modified it slightly after reading an article about the simple pendulum by Christopher Barker of San Joaquin Delta College. There's a link to his article in the description below. Let's see this code in action. Save your file and go to the rungame.jl file. Comment out the line for the previous simulation and add a line to run the pendulum.jl file and then execute it. Pretty cool, right? Break out of the game window and go back to the pendulum.jl file and try changing some of the settings. For example, try different settings for the initial theta. Also try using different lengths for the rod. For this simulation, we assumed no friction, so this pendulum will continue to swing forever. If you want to make this simulation even more realistic, it's easy to add some friction to your model. You can see that this pendulum is slowing down, and it will eventually stop moving. Even though this simulation is more realistic, it's somehow less satisfying. There's something satisfying about seeing a pendulum swinging in perpetual motion, so I'm going back to the frictionless simulation. Concentrate on the blue circle. Well, that's all for today. If you made it this far, congratulations. My only quibble with this particular simulation is that the line representing the rod is so thin that I can barely see it. Currently, there's no way to increase the line thickness or stroke in Game 0. Also, there's no way to create video files in Game Zero, so you will need to use a third-party screen recorder to capture your simulations. I'm using OBS Studio, which is a free desktop app, but there are several different screen recorders available, so I'm not endorsing one over the other. I know that I went through these examples very quickly, but my intention today was to generate as much code as I could and make it available for you, since there's not a lot of documentation available for Game Zero yet. Hopefully, having access to my code will make it easier for you to get started on creating your own custom simulations. There's a lot more material to cover regarding Game Zero, but I've already made 3 Game Zero tutorials, and we're getting close to the end of this series, so I haven't decided what to cover next. Stay tuned to find out what comes next. Thanks for stopping by. I would especially like to thank all of my channel members. Your support is what makes these videos possible. If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more Wholesome Julie tutorials, please be sure to subscribe and hit that bell. If you like what I do, then please consider joining and becoming a channel member. New tutorials are posted on Sundays/Mondays. Thanks for watching, and I'll see you in the next video.